Hey Rebecca, I know my social media video is like a couple days overdue, but I just haven't had any good ideas yet. You can't rush artistic genius. I've got an idea. Hi everyone, I'm Arrow. I'm the collections technician for natural history here at the Manitoba Museum, and today we're going to be talking about eyes, but not my eyes and not your eyes. Today we'll be talking about the compound eyes of insects. If we really want to look deep into the eyes of an insect, our regular eyes and camera lenses are not going to do the trick. Using a focus stacking setup with our usual macro lens, we can get some pretty good photos of entire insect specimens, but to get a closer look, we'll need something a bit more exciting. Fortunately, the natural history team just got some fancy new microscopic lenses that will mount directly onto our digital camera, and those will let us take a really good look. Insects are really neat in that they have two different kinds of eyes: simple eyes, which are also known as ocelli, and compound eyes. In most adult insects, ocelli are responsible for detecting overall changes in light levels rather than producing images. They're usually located on top of the head in a pattern like a triangle, here and then here. And they are used in flight for detecting the differences of light. So if the insect tilts towards the ground this way, the left one picks up a darker image because it's pointed at the ground, the right one picks up a brighter image because it's pointed at the sky, and then it can right itself in 3D space. On this wasp specimen, the black ocelli really stand out against the surrounding orange exoskeleton. Compound eyes are a bit more complicated in terms of their structure and function. As you can see, they usually take up much more space on an insect's head than the simple eyes. Compound eyes are actually made of many structures, collectively called ommatidia. At this level of zoom, we can clearly see the top of each ommatidium as the individual structures on the surface of the compound eye. But what we can't see below the surface is that each one of these is actually the top of a narrow tube. Light passes through the cornea at the top of the tube and interacts with photoreceptor cells inside the tube. When these cells are exposed to light, they send information to the insect's brain, which combines it with signals coming from all the other ommatidia to create a cohesive image that the insect can use to navigate its surroundings. Keep in mind, this is a simplified explanation. There's a lot of anatomical variation between different groups of insects when it comes to compound eyes. For instance, some have eyes that are really well adapted to night vision, while others have eyes that are adapted for high-speed aerial hunting. If we look further afield to other arthropods, compound eyes can be found in modern crustaceans like lobsters, shrimps, and crabs, as well as extinct groups like trilobites, sea scorpions, and radiodonts. The Manitoba Museum favorite radiodont, Mosurophentonii, which right now you can see in our foyer space, probably had compound eyes on the sides of its head, though a fossil with the right details to confirm the presence of ommatidia has not been found yet. Thanks for taking the time to learn about insect vision with us today. What should we put under our fancy microscope lenses next? Let us know in the comments.